This video is a very brief introduction to polarization to prepare you for the polarization lab in intermediate lab. The picture up in the top right is one of my favorite examples of using polarized light. It's showing light passing through crossed polarizers that are around a piece of birefringent material that's rotating different colors of light differently. And so we see the beautiful magenta, blue, and yellow all at different positions in this crystal that happens to be a piece of aragonite that we grew in the lab. All right, so the learning outcomes for this lab are to become familiar with linear and circular polarization and to investigate ways to alter the polarization of light. This is, as the previous picture shows, polarization is really fascinating, and polarization is around us everywhere. You don't realize how much light is polarized in all parts of your world. There are a few different lab objectives. Some of them are more involved than others. This is an exploratory kind of lab. The first lab objective is to determine the polarization plane of the laser. You started doing that in some of your other labs, and we'll do it in a slightly different way this time. The second objective is to determine the transmission axis of the polarizer and the fast axis or slow axis of the quarter wave and half wave plate that are provided. If you don't know what they are, can you find them? This is the question. The next objective is to generate a circularly polarized beam using any of the optics that you have, any or all of the optics you have. And of course, explain what you do in order to check that it really is circularly polarized. Then you'll reflect a linearly polarized beam with its polarization at 45 degrees off of a mirror, basically at right angles, and determine the ellipticity of the polarization of the reflected light. So in other words, what happened? What happened at the reflection off of the mirror? And the last objective is really just a fun game, and you will read through this particular experiment and try it out. So, brief introduction to polarization. We've talked already about how light is an electromagnetic wave, and that means it has an electric field and a magnetic field. And the polarization of light actually refers only to the direction of the electric field. It's just been decided that we will refer to the electric field as our polarization direction. So in this case, the picture would be linearly polarized in a, let's say, vertical direction. Here's an example of a linearly polarized light wave on the left. The electric field is oscillating up and down. And today we'll get into circularly polarized light in more detail. So let's look at the picture on the right. The GIF is showing that the electric field vector is going around in a circle. Now, note that the black arrow that's rotating around describes a complete circle. And you can't see that with your eyes because that electric field is changing very, very fast. Just like we can't see that the electric field is oscillating up and down in a linearly polarized wave. However, we can see that there are equal amounts of horizontal and vertically polarized light, for example, in a circularly polarized beam. Some particular examples of using polarization. Some of you probably have sunglasses that are polarized, and they're designed such that they take incoming light, which may be polarized in many directions, and they only pass vertically polarized light through the sunglasses, and that's because they're intended to block the majority of light that's around you, which is horizontally polarized. Another example where you might see polarized sunglasses or polarized lenses is in 3D glasses. These are a little bit kind of old. The 3D glasses you use now would be different, and that's how 3D glasses work in a movie theater. So let's get a little bit into the electric field description of polarization. This will not be necessary explicitly in explaining today's lab. I want you to emphasize using field vectors and vector components without writing out the full description of the wave. You are welcome to, however. So if we have a particular electric field that's E naught e to the I kz minus omega t, we can write that E naught field vector as two orthogonal components. Right? So our electric field vector E naught that we see over here on the right has two orthogonal components, one that's along what we've called the x-axis and one that's along what we've called the y-axis. And we can take any two perpendicular components and break up our electric field into those two perpendicular components. We call the angle of this electric field as defined from some axis. Where I drew theta here, the electric field would be defined relative to the y-axis. And in that, I did that because we can also explain that the amount of intensity that would be transmitted through a particular polarizer with its polarization axis along the y direction, the amount of intensity transmitted would go as I naught cosine squared theta. This is review if you've seen this information before. If you haven't, don't worry right now about dealing with intensity and the cosine squared theta term. Now this is going to be relevant for our labs this week. We need to define what we're going to call the plane of incidence. And the plane of incidence is the plane in which all incident, reflected, and transmitted rays lie. So let's just get oriented to this picture here. Let's imagine you're looking down on your laser beam, this red line, and it's reflecting off of a piece of glass. And some of the light will reflect here along this red line. Some of the light will be transmitted into the glass here. And we will call these three rays the incident, reflected, and transmitted rays. Now this whole plane is called the plane of incidence. And the angles at which we define the incident, reflected, and transmitted angles are defined relative to the normal, which is this dotted line, perpendicular to the interface. So let's start with perpendicular to the plane of incidence. An electric field that is perpendicular to the plane of incidence is going to be, in this case, in and out of the page. So I've drawn that here with a circle and a dot in the middle to show that the electric field is coming out of the page. The magnetic field is pointing off this way. The reflected electric field is still coming out of the page, and as is the transmitted electric field. So this in and out of the page would be perpendicular to the plane of incidence. If we want to define parallel to the plane of incidence now, our electric field is pointing, in this case, in this direction, in the plane of incidence. And as it's transmitted and reflected, it is still in the plane of incidence. So now we have perpendicular to the plane of incidence and parallel to the plane of incidence. This allows us to do something really interesting when which we'll understand more as we study reflection. And so something that you've learned in your optics class and in your electricity and magnetism class is that dipole radiation isn't emitted along the axis of a radiating dipole. So think about that for a moment. A radiating dipole is just a charge that vibrates back and forth, and it does not emit any radiation along the axis of that vibration. Well, reflection is actually the same thing as re-emission from the dipoles in the medium. So if this is our piece of glass that we're reflecting light off of, reflection is simply a vibration of the atomic dipoles in the glass and then re-radiation from that vibration. And I've drawn here a particular angle of reflection that coincides with the oscillating angle of the dipoles, and therefore there is no radiated or reflected light. So let's go through this. We've got an incident electric field that's pointing in this direction. The light comes towards our medium, it bends a bit, and now it's making dipoles vibrate along this red double-sided arrow. Well, those dipoles can radiate just fine into the medium, but they cannot radiate this way, which is the direction that the light must reflect. Therefore, There is no light polarized like this that's reflected. So if you had a beam that is completely polarized, in this case parallel to the plane of incidence, it would not reflect at this angle. And we call this particular angle Brewster's angle. It's defined as the angle where the transmitted light is perpendicular to the reflected light. So this angle between the reflected and transmitted beam is 90 degrees. Now let's jump from Brewster's angle and polarization by reflection to circular polarization. So there's a lot of waves written here. And again, we've got our general electric field that's an E naught, which has two components, an x component and a y component, times our oscillating term, e to the I kz minus omega t. And notice that now we've also got this E naught x, which is the magnitude, and the e to the I phi x and e to the I phi y. In other words, we now have a phase term for both the x and the y components. Well, in circularly polarized electric fields, the x and the y components are out of phase by 90 degrees. And so we write that in a couple of different ways, like this. And let's see a picture of that electric field. One more step here. We can also write this as a cosine and a sine term, our x and our y components. One more picture. So if we looked at that electric field coming straight towards us, the tip of the field vector would describe a circle. And we would see that we would have equal amounts of the x component and the y component. We wouldn't be able to tell that they were out of phase. Instead, we could just see that there were equal amounts of any two perpendicular components of that field. This is a strong hint for figuring out whether an electric field is circularly polarized. This is the description for right circularly polarized and left circularly polarized, which actually will be important, but you can't see it unless you do a particular trick, which we'll play with. All right, well, there are lots of polarizations between linear and circular, and they look something like this. They're elliptical polarization, where instead of a complete circle, the electric field vector traces out an ellipse. The x and the y components are now different lengths, and the phases may be different. The phases are not equal to pi over 2. So we write that in a general way like this, where there's a phase difference, delta phi, between the x and the y components. Okay, so one thing that is really fun about polarization is birefringence. So birefringence means double refraction, means that a material has two indices of refraction, an ordinary and an extraordinary. This happens because of particular crystal structures that result in two unique indices of refraction. And what this does is it causes polarization of light to change when it passes through that material. So this, again, the same picture that we saw at the very beginning, what we're seeing here is a birefringent piece of aragonite that we're seeing it illuminated by light that's passing through two crossed polarizers. And when we see colors, it means that that color of light has had its polarization rotated by 90 degrees. Calcite is just another another type of material that I particularly like. So here's a couple pictures of calcite. Picture on the right is actually calcite and vaterite. So the reason we just talked about calcite is because calcite is one of the materials that is used to make what we call wave plates. Wave plates are birefringent materials that are intended to make a specific phase change between two field components. So a half wave plate is one of the types we'll be using, and a half wave plate creates a phase change of, guess what, half of a wave. Half of a wave is either a phase of pi or a distance of lambda over 2. And there's some other math. This is just to refamiliarize yourself with the phase change and the difference between two indices of refraction. What a half-wave plate is for is to rotate polarization direction of linearly polarized light. And it does this by creating a phase change between orthogonal polarization components. And in the end, our polarization direction is rotated by 2 theta, where theta is the angle between the polarization of the incident light and the axis of the half-wave plate. So here we have a half-wave plate that's set vertical, and our light is at 45 degrees. The light comes out, rotated by 90 degrees, so it's now at minus 45 degrees. So another picture on the left here, start with vertically polarized light, and we come out with horizontally polarized light. We would assume in this case that our wave plate was at 45 degrees. We can see the little X's here are intended to be at 45 degrees, showing that the axes are at 45 degrees relative to the vertical and horizontal. A quarter wave plate creates a phase change of a quarter of a wave, which is either pi over 2 or lambda over 4, quarter of a wave. And there's some more math about it. What it's intended to do is change linearly polarized light to circularly polarized light, or circular to linear. So if we start with vertically polarized light, goes through a quarter wave plate, we could come out with circularly polarized light. If we sent in circularly polarized light, we could come out with vertical. This complete change only happens when the angle of the wave plate axis relative to the incident light is 45 degrees. So if our wave plate fast axis is set at 45 degrees relative to the incident light, we will get circularly polarized light. All right, so a couple applications. We just talked a lot about this cross-linear polarizer with the birefringence here, but you also see this when you see when you're wearing sunglasses and you see like an interesting pattern in a windscreen or windshield or any other kinds of plastics. And that's pretty fun. The picture on the right is a rotating piece of birefringent calcite that is rotating because circularly polarized light is shining on it. The little clip is in a loop, that's why it jumps periodically. So circular polarized light really does things. All right, we are not doing a full live video for the equipment because it's the same type of equipment you've been using the last couple of weeks. What you have here is a couple of new mounts. One is a rotation mount on the right. You've seen these with some of the optics already. We'll do some work with the rotation mounts with either wave plates or polarizers. And the piece on the left is something like either a glass cube or a prism that we will use to reflect light off of to test when light is polarized. Right, your pre-lab questions are to go through a couple of your objectives. So the first pre-lab question is to sketch the beam path for objective 4 and really describe what you expect to see. Objective 4 says we reflect a linearly polarized beam off of a mirror, and what happens? The next objective is dealing with passing a linearly polarized beam through a sequence of wave plates and polarizers and reflecting it back on itself. And I'd like you to think about what you think might happen. Remember that you can come and talk about the lab before the lab. And when you get to lab, first just compare your pre-lab and your hypothesis. I encourage you to not take very long on your hypotheses because it is, if you don't know what's going to happen, you really don't know what's going to happen and you should just try it. Be sure to sketch your diagrams initially and also be sure to check your laser alignment. And enjoy the lab.